Hey, today on Flippin Science we're going to look at metal reactivity and production. So science understandings we're going to look at: the occurrence of metals in combined or uncombined form in the Earth's crust is related to the reactivity of the metal. The method used for the reduction stage of the production of a metal is related to the reactivity of metal and the availability of energy. And given the position of a metal in the activity series, predict whether the metal is likely to occur combined or uncombined in nature. Predict and explain the likely method of reduction of the metal compound. And explain the benefits of one method of reduction compared to another given sufficient information. So metals are usually fairly reactive and they oxidize when they react. So here we have a metal, it's going to metal ions and it's producing a certain number of electrons. The more easily it does this, the more reactive the metal is. And conversely, the more easily it does this, so produces electrons, the more difficult it is to reduce the ions of the metal. So going back the other way can be quite problematic if it's a very reactive metal. And we can rank our metals in order of reactivity in terms of how they react and how easy they are to oxidize or reduce their ions. So here's some activity series. So at the top here we've got lithium, down the bottom we have gold. It's saying here lithium and potassium, barium, so on, they never occur in their free state. That means you'd never just dig up a pile of sodium, for example. It's already reacted with something else in the environment. Some metals in the middle here you can find free in nature every now and then. Then others that are even less reactive, you find them readily in nature. So gold, silver and platinum, for example, because they're not very reactive, they don't react with any other elements in nature to form compounds. If we look at how they react, you can dunk these in acids and they'll release hydrogen, so the ones at the top of the activity series. The ones down the bottom, they don't react with acids readily and don't produce hydrogen. So most metals that you find in the environment are found as minerals. That means they're combined with other elements. Some, however, you find them as their mineral because they don't react very readily. So if we look at gold, silver and platinum, for example, the ores that they come from are gold, silver and platinum ore. They don't have a particular name necessarily because they're not reacting with anything in the environment. So you usually just dig it up, combine with quartz and other things in the environment, then you separate out the quartz from the precious metal, and that's how you find it. As we go up the activity series, we start looking at lead, zinc, iron and copper. We can see that we're starting to get different names here, and that's because we're combining with different elements. In the case of galena, sphalerite and pyrite, we're combining with sulfur. So these ores, galena, sphalerite and so on, that's where we get our lead and zinc and so on. We have to extract the lead and zinc from the ore to have the useful metal. So if we look at the table on the previous slide and the reactivity series, you can see that the more reactive a metal is, the more likely it is to be found in a combined state in the Earth's crust. And what I mean by that, it's more likely to have reacted with something in the environment. So highly or even moderately reactive metals can be found combined with other elements such as oxygen and sulfur. So down here, this is a picture of galena. So this is where we get our lead from. So it's lead sulfide with other bits and pieces. So it's combined with sulfur in the environment. The less reactive metals don't react with the elements because they don't easily oxidize. And if they don't easily oxidize, they don't produce ions. And if they don't produce ions, they're not going to stick with other things in the environment. So down here we have gold on a quartz substrate. So the gold itself, it's not reacting with anything. It's just stuck as part of that rock there. Metals that are less reactive than aluminium, you can use a reducing agent like carbon rather than doing electrolysis. So if we look at, say, zinc and iron, you can reduce their ions using carbon and carbon monoxide rather than having to electrolyze a salt. You can electrolyze a salt solution for metals up to zinc. So copper, for example, they use a copper sulfate solution that's electrolyzed to produce copper. So for these ones in here, you can use a salt that's in solution and reduce the metal ion from the salt solution. Above zinc, you need to use a melt, which means you have to produce a salt and then melt that salt at high temperatures and then electrolyze that. The reason why you have to do that is if you used water in the mix, as you do with the ones in here that use an aqueous salt solution of, the water will be reduced in preference to the metal that you're trying to reduce. So here's a nice diagram that sums up the reduction processes for metals. So if we look at very active metals, they use a molten salt, so molten chloride or a molten oxide. For metals between zinc and lead, they can use the carbon or carbon monoxide to reduce it. For things like copper, And some of these in here, you can also use a salt solution. You can reduce the metal ion from a salt solution. And then down here we've got silver and gold. They're found natively. They don't react with anything in the environment, so you don't have to worry about doing a reduction process at all. In terms of environmental effects, the reduction part of the process requires an awful lot of energy, and so it's the most expensive part of the metal production process. So if you use a blast furnace, so down here we have a blast furnace that's used for things like iron, you need to heat that up to high temperatures, and you need to provide things like gas or electricity to produce the really high temperatures there, and that can be quite expensive for the manufacturer. If you need to electrolyze a melt, more than 50% of the energy that you need is just used to keep the melt at the temperature. So for aluminium, we saw it needed to be at around about 1000 to 1200 degrees Celsius, the aluminium oxide cryolite mix. Just keeping it at that temperature requires half the energy in the whole production process. So we talked about a blast furnace. This is a blast furnace, and that's how you can produce very low quality iron. So at the top of the blast furnace, you insert your iron oxide coke, which is carbon and limestone. That gets put in the blast furnace, which is at quite high temperatures. As it passes through the blast furnace, the coke produces carbon monoxide and carbon dioxide, and they're the reducing agent for the iron. So here's the equation over here. So iron oxide plus carbon monoxide goes to iron plus carbon dioxide. So the iron produced trickles down the sides of the blast furnace and collects down the bottom. You get a layer of slag being produced. That's your silicates that are your waste products. And you tap off the iron down the bottom here. So again, keeping this blast furnace nice and hot, that's where the energy cost is in this process. So one of the things you need to talk about is using a solution versus the blast furnace or a melt. If you can, you use an aqueous solution, because an aqueous solution is very cost effective. The solution that you have, and this is for copper production down here, the solution that you have there, it's only kept at 40 to 60 degrees Celsius, so that doesn't require a lot of energy to do. Whereas if you need to use a melt, you need to heat up the salt to its really high temperature before the ions will separate and it will melt, and that requires an awful lot of energy. In the blast furnace as well, you need to provide a lot of energy to heat up the blast furnace so that it's effective at turning the carbon into carbon monoxide in order to so that it can reduce the metal ions. So if you can, use an aqueous solution. So let's have a look at some questions. It says, first one says, identify a suitable electrolyte for the production of sodium metal. Sodium, if we look at a metal activity series over here, and I stole this from one of the exams, sodium is quite high in the activity series. Because it's quite high, you won't be able to use a sodium solution, so you can't use sodium chloride solution to do this. So you're going to need a salt, so a molten salt. So molten sodium chloride would be a good electrolyte for the production of sodium, for example. Second question here says, copper can be used to make catalysts necessary for the production of methanol. Predict the likely method of reduction used to convert copper mineral into copper. If you look at our activity series, again we can see copper is right down the bottom of these metals listed. So that means we could use something like carbon or carbon monoxide as a reducing agent. In reality, what is used is a copper solution. Electrolysis for copper sulfate solution is used in industry to produce copper. So that's a likely method because it is the method that's used. Another part here says copper can be produced by heating its oxide with carbon. Explain why a similar method cannot be used to produce aluminium. So again, if we have a look at our activity series, we can see copper's down the bottom and aluminium is in the middle here. So carbon isn't a strong enough oxidizing agent to reduce aluminium ions. So that's the simple answer there. Because copper is less active, it's more easily reduced. So we can use carbon as its reducing agent, whereas aluminium is more reactive, which means it's more difficult to reduce. So we need to use a stronger reducing agent than carbon or carbon monoxide. Part 2 says, state one reason why the manufacturer uses zinc sulfate solution rather than molten zinc oxide as the electrolyte for electrolysis. By using zinc sulfate solution, you don't need as much energy. If you used a zinc oxide melt, you would have to heat up the zinc oxide salt to a ridiculously high temperature before it's melted, and that would require a lot of energy and therefore cost to the manufacturer. By using a zinc sulfate solution, you don't need as much energy because it's a solution. So the zinc and sulfate ions are there present. You don't need to heat it up to break it up. So it uses less energy, which is cheaper for the manufacturer.